So yeah, data flow modeling in Verilog. So for small circuits, the gate level modeling approach works very well because the number of gates is limited and designer can instantiate and connect every gate individually. For example, in previous sessions we have developed the full adder, half adder circuits with the help of this gate level modeling, and there were around 9 to 10 gates like that. So it was simple for us to use this gate level modeling for this small circuits for but in the cases of big circuits where they are like 50 to 60 gates, it is not feasible to use this gate level modeling because we have to instantiate every gate, and we should be careful while instantiating the gate, and we should be careful while declaring the and connecting the logics and wires. We have faced some issues also for the small gate. Only we have issued that we have by mistakenly connected some wire, so we are not getting output. So in these scenarios, this gate level modeling will not be feasible when the design is very large and the designer cannot so it is not possible for the designer to instantiate every gate in case of larger designs. So however, in complex designs the number of gates are very large, so the designers can design more efficiently if they concentrate on implementing the function at a level of abstractions higher than the gate level. So in case of in case of larger designs, instead of a designer focusing on the gate level abstraction, he can focus more on the data behavior or the flow uh, data flow. So in case of larger circuits, the designer, instead of focusing or concentrating on on the gate level abstraction, he will concentrate more on implementing the function at a level of abstraction higher than the gate level. So the data flow modeling provides a powerful way to implement a design. So basically, this data flow modeling more focuses on implementing a function rather than depending upon the gates, individual gates. It will depend more on implementing the function. So with the help of this data flow modeling, we can design larger circuits. So data flow modeling provides a powerful way to implement a design. So Verilog allows a circuit to be designed in terms of data flow between the registers and how a design processes the data rather than instantiation of individual gates. So rather than instantiating individual gates like in gate level modeling, here in case of data flow modeling, the designer can decide how the data can flow between the different registers and how a design processes the data. So if we have a design, so this is our design, and if we have some inputs and outputs to our design, so rather than the designer focusing on the gates involved in this design, he will focus more on the functionality of the design. He will more focus on the functionality of the design, and he will code the RTL code accordingly, and the synthesizer will take care of generating these gates at gate level netlist. That level is called gate level netlist. So the code which the designer writes, the synthesizer will or the tool will convert that code into this gate level netlist, and it will convert the design into gates. So now the designer in data flow modeling uh, concentrates more on the functionality of the design. So in digital design community, the term RTL, register transfer level design, is commonly used for a combination of data flow modeling and behavioral modeling. So RTL, that is register transfer level modeling. Transfer level modeling is a collection of these two abstractions, that is data flow modeling and behavioral modeling. So there are two types of abstraction involved in this RTL. One is data flow modeling and another is behavioral modeling. If wanted, we can use gate level modeling, but mainly we focus on data flow modeling and behavioral modeling. So the data flow modeling will focuses more on the flow of the data between the registers. So is this clear for everyone?
Yeah, yeah.
Yes.
Yeah, thank you. So this is the introduction to data flow modeling, why we are changing our focus from gate level modeling to data flow modeling. So coming to data flow modeling, we have a concept called continuous assignments. So what is meant by continuous assignment? So a continuous assignment is the most basic statement in the data flow modeling used to drive a value onto the net. So a continuous assignment, so coming to the continuous assignment. So in data flow modeling, we use this continuous assignment statements. So if you find anywhere this continuous assignment statements, then blindly you can fix that the design is the abstraction level is data flow modeling. So if there is a usage of continuous assignment statements, then the abstraction level is, then the RTL code written is in the data flow modeling abstraction level. So in this case of continuous assignments, the values are continuously driven onto the nets only. So in case of continuous statements, the values are driven continuously into the nets. So a continuous assignment replaces gates in the description of the circuit and describes the circuit at higher level abstractions. So a continuous assignment starts with the keyword assign. So let's discuss the syntax for this continuous assignment. So here we will have, in continuous assignment, we will use the keyword assign for assigning the values. Say suppose, so here first point to remember is we will use only the nets in the continuous assignment to store the value. So on the left hand side, we will use only the nets. Regs are not allowed on the left hand side. I'm talking about left hand side. So on the left hand side, we can use only the nets. Regs are not allowed in the continuous assignment statement. So for let's say suppose let's declare a net, say wire A. So wire A is a net. So if we want to store a value in the net A, then we will use the keyword assign. In continuous assignment statement, we will use the keyword assign followed by the net A is equal to, we can store, we can write. So here I will take three cases. First case is storing a value. Here, let's say suppose 4. So I'm storing a value of 4 in this net. So in the first case, I'm storing a direct number in the wire. So this is a continuous assignment where we are storing direct number in a net. And coming to the second case, let's say I declare a reg C and a wire D. So I want to store the value present in C into D. So I will write assign. So assign, in continuous assignment statements, we will use the keyword assign followed by the wire D is equal to C. So this is how we store the value of C, that is the value stored in the reg, into the wire. So this is a continuous assignment where I am assigning the value of a reg to the wire. I am assigning value stored in reg to a wire. So this is the second case. The first case is we are storing direct value to the wire, and in second case we are storing the value stored in the reg to the wire. So like this, we will write the continuous assignment statements, and if we want to try like assign C is equal to D. So is this valid? So is it valid or not? Assign C is equal to D. Can anyone? So this is not valid. So we cannot have a reg on the left hand side. So we cannot have reg on left hand side. This is the rule in the continuous assignment statement. We can only use wires, we cannot use reg, we can only use net data type on the left hand side. We can only store the value into the nets, not in the regs. So this is the point I wanted to discuss. And coming to the continuous assignment characteristics, the left hand side of an assignment must always be a scalar or vector net, or a concatenation of scalar and vector nets. It cannot be a scalar or vector registers. This is what we are discussing. Here on the left hand side, we can have only nets. It can be a scalar. So on the left hand side, it can be a scalar or a vector nets only. Only the scalar and vector nets on the left hand side are allowed. We cannot use scalar or vector regs on the left hand side. It is not valid. We will get an error. So scalar we already know that a single bit. Vector means we have discussed the concept of vectors, like say suppose if we want to declare a vector of wire type, then we'll take some vector like this. I'm taking 3 down to 0. Like this, we can declare a vector and we can store the value into this vector. So say suppose if I have declared wire 2 down to 0 C and reg 3 down to 0 D, and I want to assign the value of D into the C, then I will write assign C is equal to D of 2 down to 0. If I want to store uh, the value from 2 down to 0 into the C, then like this I can store it, or I can simply write assign C is equal to D. Then D will be truncated. So this is how we will store the values in this continuous assignment statements. Now coming to continuous assignment statements are always active. The assignment expressions is evaluated as soon as one of the right hand side operands changes and the value is assigned to the left hand side net. So here for say some example, if we have wire A and reg B, or else we can also have wire B also on the right hand side. Right hand side can be a reg type or a wire type, no problem, but left hand side we should maintain only a net type. So assign A is equal to, now I am taking B, B as a wire type, assign A is equal to B. So whenever there is a change on the right hand side, whenever there is a change on the right hand side, it will immediately affect the left hand side. So whenever there is a change in B, then immediately the statement will be executed. So say suppose if we are writing a test bench, and in the test bench we are writing B is equal to 0, and after 10 time units we are writing B is equal to 1. So here B is equal to 0, we are getting B is equal to 0, so the statement will be executed. And after 10 time units again we are getting B is equal to 1, then immediately the statement will be triggered and it will be executed. So that is what it is written here. So continuous assignments are always active. So the assignment expressions is evaluated as soon as one of the right hand side operands changes and the value is assigned to the left hand side net. So is this clear for everyone? Is this clear, right? Can we move forward?
Yes, yes.
Yeah.
Yeah.
So the operands on the right hand side can be registers or nets or function calls, and registers or nets can be scalars or vectors. So as we have discussed, so assign A is a wire, and right hand side can be a register or it can be a wire of scalar or vector, no problem, scalar or vector, and it can be a function call also. I will discuss these functions and tasks in upcoming sessions. So remember that right hand side can be reg, wire, or a function, and left hand side should be of type wire only. Wait a minute. So here there is an example. So continuous assign out is a net, and I1, I2 are the nets. So this here in this example, left hand side is a net, LHS is a net, and RHS is also a net type. And we have continuous assign for vector nets. Here they are using assign ADDR 15 down to 0 is equal to ADDR underscore 1, sorry, ADDR 1 underscore bits 15 down to 0 into ADDR 2 underscore bits 15 down to 0. So here ADDR1 underscore bits is a rect type, and ADDR2 underscore bits is also a rect type, and we are multiplying this 2 and we are storing it into a net type. So this is the example, one of the example for the assignment of continuous assignment statements. So this is all for today's session. So in this session we have discussed what is data flow modeling and why we are changing our abstraction level from gate level modeling to data flow modeling, and what is the basic statements used in data flow modeling, and what is continuous assignment, and what are the data types which are used in this continuous assignments. So yeah, if you have any doubts, you can ask me.